Okay, so last time we were talking about enantiomers and chirality and the fact that sometimes the only difference between molecules is the spatial arrangement of the groups attached to certain carbons we call chiral centers. We looked at this example, how at this particular chiral center here in both molecules, that is the only difference between these structures. One has this group coming out of the screen at you, the other has the group pointing away. Does that cause a difference in their properties? If we're thinking about their polarity, or if we're thinking about their solubilities or boiling points. Well, if we look at their physical properties, if I have a pair of enantiomers, they end up with the same physical properties. The only difference is a slight difference in the direction and space one of the groups is pointing. It doesn't change the overall polarity of the structure. It's the same for both molecules. They're going to have the same solubility in water, same energy required to break their intermolecular attractions if you want to melt or boil a substance. So when you have a pair of enantiomers mixed together, it's really difficult to know. They have the exact same properties. You can't use the boiling point or melting point range like we've been talking about to assess the purity of compounds. We can't use chromatography like we did in Lab 3 to rely on differences in polarity to allow some compounds to move faster through silica gel than others or through an ion exchange resin. Because their properties are so similar, it's difficult to even know if they are present together. So one experiment you can do to determine the purity is to look at optical activity. One property that is different between these enantiomers is the way that light will be impacted as it passes through a sample of the R versus the S enantiomer. So that's what we're going to talk about right now. So what we need here is not just any old light that's shining out of your light bulb, right? If I have a light source and it's shining out light, the light has this electrical and magnetic field, so it's like a wave. So I could imagine the magnetic field in the plane of the screen in some of the rays of light that are coming out of the light bulb. In others, the magnetic field might be rotated at an angle, or it might be parallel or perpendicular to that, I mean. So some of the lights, it's really hard to show on a two-dimensional screen. Some of the lights coming out in one direction or one plane, and other versions of the light are coming out in a different plane. So if this is like, this wave is coming out as a flat structure, another wave would be coming out on a plane perpendicular to that, and every plane or angle in between would also be present. So before you pass the light through your sample to determine whether you have R or S enantiomers, what you need to do is pass the light through this polarized filter that will only allow light coming through on one plane to pass through the filter. So if this is my normal light, some of the lights on this angle, some of the lights on this angle, some of the lights on this angle, that light all gets blocked. Only the light that's coming through at a certain plane can pass through these slits and then make it out the other side. So first I have to take the light and do what's called plane polarizing, or plane polarize the light, meaning the light's only coming through my sample on one plane. I don't have the light traveling on other planes making it through there. So then I'm going to take that light as it passes through the filter. It's all coming out on one plane, right? None of the light coming through in this direction or in this direction or in this direction can make it through the filter. Only one precise plane makes it through. that light that passes through is all going on one plane, and then it passes through your sample. So your sample is inside this tube. It might have the R enantiomer, it might also have the S enantiomer, it might have a mixture of both, and so that's what we're trying to determine. So if the light's all traveling on one plane and as it passes through here, let's just say I only have one enantiomer. I only have R enantiomer molecules in this sample, so that would be just these molecules, and the other ones aren't present. The light that's traveling through on a certain plane, because it went through the filter, and the filter only lets through a certain plane, light coming through at a certain plane, once it starts to pass through the sample, it's rotated, and it comes out the other end of the sample on a different plane, rotated by some degrees. And then the instrument measures how much the light was rotated. So optical activity measures the degree to which the plane of the light is rotated. It's not rotating the molecules. The molecules are rotating the light by some degrees. If it's a 10-degree rotation, that's not very much. A 90-degree rotation is a lot. It could be 180 degrees. So to some degree, as that light passes through there, it's going to be rotated. It's going to depend on how many molecules there are and how long the tube is. Right? Every molecule that the light hits rotates it a little bit more. And so we have to set our instrument in a standardized way so that all the tubes are the same length and the molecules are present in a certain concentration if we want to make comparisons between molecules, which is what we want to do. So it turns out when you do experiments that if I fill that tube with only R, it will rotate the plane of the light by some degree, and the S will rotate the plane of the light in the opposite direction. So if I have R present and no S, and it rotates it to the right, or a positive degree, if I then swap that out and put S in, it would rotate it in the opposite direction by the same amount, assuming I have the same length tube and the same number of molecules present. So because enantiomers rotate light in opposite directions at the same temperature, the degree to which the light is rotated depends on how much of the S is present versus how much of the R is present, which we'll see in a minute. So we also said it depends on how many of the molecules there are and how long the tube is. So as long as all of our tubes have the same length, and as long as all of our samples have the same amount of material per space, per unit of space, if we standardize all that, we can get something called the specific rotation. So the specific rotation is standardized to make sure that all the experiments are done with the tube with the same length and the same amount of compound and the same amount of solution. And that way we can compare measurements. If I do an R enantiomer, its rotation will be in one direction. There's no way for me to know which direction if I haven't done any experiments with R previously. But I do know that if I have R, it will rotate in the opposite direction from S to the same degree. We are talking about enantiomers here, though, right? So if I had this molecule, is that R or S? Well, we talked about that last time. We said prioritizing 1, 2, 3, going clockwise. This one would be R. So that will rotate plane polarized light in one direction. Maybe, who knows, 10 degrees. I don't know. We'd have to do that experiment. If I take the opposite enantiomer, where the chlorine has the opposite configuration, which would be S, that would rotate the light in the opposite direction by the same amount. But if I just take some other random compound, maybe put a bromine here or something, the degree to which the bromine rotates the light is not related to another molecule, right? So just because this one is R, it doesn't mean that this R will rotate the light the opposite direction from this S. They have to be enantiomers of one another in order to say with certainty that one will rotate the light equal and opposite direction from the other. So here we've got two enantiomers. We have some data from some experiments that were performed. The specific rotation at 20 degrees Celsius using a specific wavelength of light, also assuming that the path length is the standard path length and we have 1 gram of this per milliliter of solution. We find it rotates the light counterclockwise 23.1 degrees. If we take the opposite configuration of the exact same molecule, so these two are enantiomers, they're mirror images of one another, they can't be superimposed upon one another, right? If I take this molecule and slide it over, this bromine's pointing away from you, this one's pointing out at you, they're not going to line up. So there's no way to line up these structures no matter how I flip one in space or rotate the bonds around. But they are mirror images. If you put this one in a mirror, its reflection would look like this one once it's flipped over. So if I can flip one in any orientation and it looks like the mirror image of the other, but they're not superimposable, then I know they are enantiomers. I can also test that because if they have the exact same name and an odd number of chiral centers, but the opposite configuration at each chiral center, that also helps me to determine that they're enantiomers. And so experimentally, this verifies what we just said. One of the enantiomers rotates the light in one direction, the other rotates it in equal amount, but in the opposite direction. Just to point out, the signs here refer to the direction the light is rotated. The signs here are not correlated with the R or S configuration. So there's no rule that says R is always a negative rotation or S is always a positive rotation. It's pretty much random. There's no correlation there. So if you want to know whether an enantiomer rotates in a certain direction, positive or negative, you have to run the experiment or have someone else have already run it and look up what the results were that they got from when they did that experiment. So this is what we were just saying. There's no relationship between whether something's R or S and which direction it will rotate light. You have to do that experiment to find out that information. All right, so let's take a look at this example here. We've got a molecule. It's got one chiral center. Is it R or S? Well, let's see. I want to prioritize the groups attached. I've got a nitrogen, a carbon, and a hydrogen. Nitrogen takes top priority. I've got these two carbons. This one, the top priority thing it's actually bonded to is a carbon. For this one, the top thing it's bonded to is an oxygen, which takes priority over carbon due to having a higher atomic number. So this would be 2 and 3. So then I want to rotate from 1 to 2 to 3. I get a counterclockwise rotation. So is that R or S? Well, normally counterclockwise is S, but that's only when the fourth priority group is pointing away from you. If the fourth priority group has a solid wedge, it's the opposite. So this happens to be the R configuration of this structure. So we've determined this one is R. How would I change the configuration? Well, I can't change it by rotating any of the single bonds or flipping the molecule over. If I measure the rotation of plane polarized light as the light passes through a sample of these molecules, at room temperature I find that it rotates the light in one direction, but when I change the temperature, it rotates the light in the opposite direction. So this is just here to demonstrate to you that the direction that the light rotates is not related to whether it's R or S. Changing the temperature is not going to change an R configuration into an S configuration. The only way to change that would be to swap two of these groups. So changing the temperature of a sample of these molecules does not change the fact that they have an R configuration, but it does change, in this example, the direction that the light is rotated as it passes through that sample. So just remember, you can't correlate the plus or minus rotation of plane polarized light passing through a sample with R or S unless you do an experiment. All right, and that's what we just said. We can only determine that experimentally. We can predict, though, the optical rotation measured for a racemic mixture. And here's a new terminology. Racemic mixture refers to a 50-50 mixture of two enantiomers. So if I did have a sample that had two enantiomers, the R and the S, mixed together in a 50-50 mixture, what would the optical rotation be? Now we just said if they're at the same temperature, present in equal amounts, one will rotate plane polarized light in one direction. We don't know whether it will be positive or negative, but we do know that its enantiomer will rotate light in the opposite direction. So if I have a 50-50 mixture of the two, half the sample will be rotating the light on a certain plane in one direction, and then the other half of the sample will be rotating it back. So there'll be zero net rotation. So we won't get any rotation if we have a racemic mixture because the two enantiomers are canceling each other's rotations of the light passing through them. That's getting canceled out. So we can answer that question. Anytime we have a racemic mixture, we know there's going to be zero rotation of the plane polarized light. All right, so what about this question? So we've got 2-methylbutane. Can we predict the optical rotation of 2-methylbutane? So let's say I've got butane, I've got a methyl on 2. So let's say the methyl is sticking out at me. How can I predict the rotation of this of the light if I pass polarized light coming through on one plane through that sample? Can I predict whether it will rotate to the right or the left or what the rotation will be? In this case, it's also zero rotation. Why is this molecule going to have zero rotation? Because it is a chiral. It's not a chiral molecule. It doesn't have a chiral center. This right here is a CH3, and this is a CH3. It doesn't matter whether I have a solid wedge or a dash wedge here. This carbon is not chiral because it's got two identical CH3 groups attached to it. None of the carbons here have 4 unique groups attached. There's no chiral center, so the molecule is achiral. An achiral molecule doesn't rotate plane polarized light. So if the light's coming through on one plane, it just continues to pass all the way through the sample on the same plane. So if you get zero rotation, it means your sample is either achiral or it's a mixture of enantiomers present in a 50-50 ratio. Any questions about that? All right, so what if I don't have a 50-50 ratio? Well, if you don't have an equal mixture of the two enantiomers, that means you have excess of one of the enantiomers, and that's called enantiomeric excess. So enantiomeric excess is where you have a little bit more of one enantiomer versus the other. And percent EE is really a way of measuring how much of the excess, the amount of excess of one enantiomer for every 100 molecules. So per the total amount times 100. So if I have percentages here, I'm interested in the amount to which one of those is in excess of the other. So this sample right here is 70% R and 30% S. How much of that is actually the excess amount? Well, if I think about this, I've got 100 molecules, 70 out of 100 are R, and 30 out of 100 are S. So if I have 30 S, if I take that 70R and I break it down, 70R is a combination of 40R plus 30R. Why am I breaking this down? Because what I want to show here is that if 30 molecules are S, or 30% is S, and I have an equal amount of R plus 40 more R beyond that, this 40 is the excess, right? 60% of the mixture is racemic, where 60% of the mixture is at 50-50 equal amounts of R and S. It's the 40% beyond that that's the excess. So I have 40 excess out of every 100 total times 100, and that gives me 40% EE. So I'm not saying that I have 40% of the mixture is R or that 40% is S. I'm saying that 60% of the mixture is at 50-50, and the 40% beyond that, the 40% of R that's left over after some of the R cancels the S, that's the excess. That's the amount that actually will affect the rotation, right? Because the 60% of that sample that's a 50-50 mixture of the two, the rotation associated with that cancels itself out. So the rotation will be 40% of what it would be if I had pure R. Right? 100 molecules of R rotate a certain amount. 40 molecules of R rotate 40% of that amount. And the remaining 60%, since it's a 50-50 mixture, it cancels itself out and doesn't matter. So we can develop this relationship here that captures that idea, and that is that if I observe a certain rotation that's a fraction or less than what it would be if I had a pure sample, I can use the amount I actually observe to figure out how much of that sample is excess versus how much of it is a 50-50 mixture. Right? So we can use this formula right here to do that. We can say the observed rotation is 4.6. The amount it would rotate if it were a pure enantiomer would have to be given or measured as well, and that's 23.1. So if I multiply that by 100, I get 4.6 divided by 23.1 times 100, and I get 19.9. So since I only have two sig figs here, we're going to round that up to 20%. So that's the EE. That's the amount that's excess in this sample. And since the observed rotation was positive, I know the enantiomer produces the positive rotation that's in excess. Right? If I had more of the other one, it would rotate the light in the negative direction more than in the positive direction. So this is rotating 20% of what it would be if the sample were pure. So that means I've got 20 molecules more of this, and the rest of the percent, the remaining 80%, breaks down in equal amounts of both. So if I wanted the enantiomeric ratio, that would mean I have 40% of this enantiomer to 60% of the other enantiomer. So 20% is excess and 80% is a 50-50 mixture. So that's how these equations work. Any questions about that? All right, so that leads us to this quiz question from today. This is basically what we just did, except we're looking at it from the opposite direction. Instead of getting the observed rotation and determining the ratio like we just did, if we're given the ratio, we want to be able to predict how much plane polarized light will rotate if it passes through a sample of enantiomers with that ratio. So the first thing I want to do is to use the ratio to get the percent excess. So what's the excess here? Well, I've got 44 molecules of R for every 56 molecules of S. So 44 of my molecules are R, they're rotating it one way. Out of the 56 molecules of S, I need 44 of them to cancel out the rotation of the 44 molecules of R, right? They'll only cancel if they're present in equal amounts. So out of the 56 S that I have, I'm going to subtract 44 because that's the amount that is actually necessary to cancel the rotation of the R enantiomer. So if I take 56 minus 44, I get 12. So what we're seeing here is 88% of this, if I add these together, 88% is a 50-50 mixture. None of that is going to cause any rotation. The remaining 12% of the sample, which is S, because there's more S than there is R, that's the excess. So I can determine that the percent excess is 12%. I got 12% more, or 12% of my sample is S, and the other 88% is half R and half S. So now that I know the percent EE, or the excess, percent EE, I can then use this formula to solve for the observed rotation. So the percent EE should be the observed rotation divided by what I'm observing if it were a pure enantiomer. So the observed rotation divided by the pure rotation times 100. So I've got the percent EE, it's 12%. And I'm going to divide both sides by 100 to get rid of that. So I'm trying to determine if I have this mixture, how much is this actually going to cause the plane polarized light to be rotated. That's what I'm solving for, the observed rotation. So how much would it rotate if it were pure S? That has to be given or inferred from information that's given. So what we have given here is that if it were pure R, it would rotate in a positive 33 degrees. So if I have excess of the S always rotates in the opposite direction from the R. So if it were pure S, it would have a negative 33 degree rotation. So then I would just solve that algebraically for observed rotation and multiply both sides by negative 33. Times 12 divided by 100 gives me an observed rotation of negative 3.96 degrees. Right, so if I had pure S, it would rotate negative 33 degrees. But mostly my mixtures are 50-50. So that majority of the molecules cancel each other's rotations out. Only a 12% of the material actually causes a rotation. So this degree of rotation is 12% of what the rotation would be if it were pure S. And that's what we see in our answer. So we should probably actually round that to 2 sig figs, so negative 4.0 degrees should actually technically be correct. I don't have more than 2 sig figs in any of my answers or numbers here. So make sure that you can work with that formula and have a conceptual understanding of what percent EE is and use that in examples. So practice those up. Alright, so last time we were talking about different types of isomers. We covered constitutional isomers and stereoisomers in general, where the only difference between them is a spatial difference, where the groups are pointing in space, and they also can't be superimposable, or they're not even isomers to begin with. And then we said sometimes stereoisomers are mirror images of one another. They're called enantiomers. Sometimes they're not mirror images, and we call those diastereomers. Right, so really there's 3 total terms that you need to be able to understand and apply to specific examples. So we want to look at that in more detail. So we talked about cis-trans isomers before in the context of a double bond. We said if we have two identical groups on the same side of the double bond, that's cis. If we have two identical groups on opposite sides of the double bond, that's trans. So what's the difference between these structures? Well, they're not constitutional isomers because they're both 4 total carbons with a double bond between the center 2, or in other words, the double bond has the same groups attached to the same carbons, right? To make one molecule into the other, I'd have to rotate this double bond, which I can't do because the pi bond would break, or I'd have to break the sigma bond here and here, and then swap these two groups and get them in opposite positions. So to do that, I'd have to reconnect the atoms to the same carbon. So I'm not changing the constitution. We're making a constitutional isomer unless I reconnect the atoms to different carbons, right? So just to point out, if I had both CH3 groups on the same carbon, this one here would be a constitutional isomer of the other two. It would be a constitutional isomer of this one, it would be a constitutional isomer of that one, because there's a difference in where the carbons are connected, not just where they're pointing in space. But for the two molecules at the bottom, the only difference is the direction in space where the CH3s are pointing. This one has it pointing up, this one has it pointing down. So once I establish the only difference between them is that they're a difference in the spatial arrangement of the groups, not a difference in connectivity, that tells me they're stereoisomers. I also want to check to make sure they're actually not superimposable, right? So I'd slide this molecule over top of the other one. Clearly, the methyl group lines up with the hydrogen. There's no way to get everything to match up, so they're not identical. So if they're non-superimposable, meaning they're not identical, but the only difference between them is the spatial difference, I know they're stereoisomers. So then I just have to look to see are they mirror images? And to be enantiomers, they have to be mirror images. The question is not whether or not they are currently mirror images. The question is, can I make them into mirror images? Can I maybe flip a structure over or rotate one of this or more of the single bonds? Single bonds can rotate, double bonds can't. But if I can rotate single bonds or flip one of the structures over, and now one is exactly what the other one would look like in a mirror, then they're mirror images. That would make them enantiomers. And that's not the case here, though, right? So if I put a mirror here, oops, and I drew what this one would look like in its reflection in the mirror would look like, the reflection of this structure would look just like the original structure. So this molecule doesn't have an enantiomer. If I draw its mirror image, the mirror image can slide right over top of the original one, which tells me that they're exactly the same and they're identical. Right? So if a structure is superimposable or identical to its mirror image, it is not chiral, which we already know because it doesn't have any chiral centers, and it cannot have an enantiomer because an enantiomer must be a non-superimposable mirror image. And so since these two molecules are not identical, these two molecules are not superimposable, but they are different spatially, but they're not mirror images, that leaves us with the answer of diastereomers. So to recognize that molecules are diastereomers, really the only effective way to do that is to rule out all the other possibilities first. You have to rule out the fact that they might be identical. They're not, because they're not superimposable. Rule out the fact that they might be constitutional isomers. They're not constitutional isomers because the difference between them is not a connectivity difference. Rule out the fact that they're mirror images. They're not mirror images because if I drew the mirror image of one, it wouldn't be the same as the other. And so then that just leaves me with diastereomers. So if the only difference between them is the spatial difference and they're not mirror images, that makes them a pair of diastereomers. So let's look at some more examples. So here I've got a ring. If I have an OH adjacent to a CH3, clearly at this carbon, it's a chiral center. Right? This direction moving around the ring is different from this direction moving around the ring. I've got an OH and I've got a hydrogen. So this OH and the hydrogen can't be in the same plane as the ring because of this tetrahedral carbon. Right? Tetrahedral carbon can never have 3 bonds in the same plane. So I have to somehow show the position in space. So we're going to talk about the different possible stereoisomers that could exist here. So let's just say one of those stereoisomers could exist if both those groups were solid wedges. Another one, maybe one of the groups is a dashed wedge and the other is a solid wedge. And another stereoisomer, maybe this one is a solid wedge and this one is a dashed wedge. And the fourth one, maybe they're both dashed wedges. So there are 4 possible stereoisomers for this compound, right? They're all stereoisomers because the only difference between them is the direction in space, either toward you or behind the screen, that these groups are pointing. So let's talk about the combinations of these and see if we can make sure we understand the differences between enantiomers versus diastereomers. So what's the relationship between A and B? Well, A and B is a pair of if we look at the structures and see that the same groups are attached to the same carbons, right? I've got an OH on one and a methyl on two in each one of these structures. So I can tell that none of them are constitutional isomers because they all have only a spatial difference. So then I want to look for the possibility of them being superimposable, right? So if I take B and slide it over on A, the methyl groups will line up, they're superimposable, but the OH pointing away is not going to line right up on top of the one pointing out at you, so they're not superimposable. So I know they're stereoisomers, which leads me to the possibility of them being either enantiomers or diastereomers. So I would probably want to make models of these and flip one over and see if I can make one look like it's the mirror image of the other. If you try to do that, in this case I highly recommend you do that, you'll find that they are not mirror images. Which means that they are diastereomers. What about A and D?
The enantiomers?
Very good. A and D are mirror images. So one kind of trick you can use is to look at each chiral center. If I've got two structures like A and D, and at each of the two chiral centers I've got the opposite configuration at both, that suggests they're probably enantiomers. But as we're going to see a little bit later today, if I have an even number of chiral centers, and I've got two chiral centers here, and 2 is an even number, it's not quite that simple. So I really have to make the models and show that A and D are actually mirror images that are not superimposable. So there's no way to slide D over on top of A and have everything line up. I could think about flipping D over like a pancake and then sliding it over on A. I want to think about all the different ways the molecules could be flipped over. It's much easier to do with a handheld model to see if everything lines up. In this case, they don't. They are mirror images. If I made a model of both and put one in the mirror, its mirror image will look exactly like the other one. So they are mirror images, which means they are enantiomers, because as mirror images that do not line up directly on top of one another, the only difference between them is that they are mirror images. What about A and C? A and C are diastereomers. Just like A and B, if I've got multiple chiral centers and one of those chiral centers is the same in both structures, but the other chiral center is the opposite from one structure to the next, that is a good sign that I've got a pair of diastereomers. So the more chiral centers there are, the more possible diastereomer combinations there are, right? Because if I take any one of my chiral centers and keep its configuration the same, but swap any one of the other ones, that's pretty much always going to lead to a pair of diastereomers. And then you could look at the other combinations, but we want to look at something a little bit more interesting here, which is a situation where we've got 3 chiral centers on my structure. So if I have a cyclohexane with 3 chiral centers, now I've got even more possible isomers. I've got 8 here. So within each green box, I've got a pair of enantiomers. So what is the pattern that I'm noticing? If I have an odd number of chiral centers, and I take my structure and redraw it, and make the opposite configuration at every chiral center, I'll make the enantiomer. So this is a pair of enantiomers. This is a pair of enantiomers, right? I take this configuration, make it the opposite, take this one, make it the opposite, take this one, make the solid wedge into a dash wedge, make the dash wedge into a solid wedge. That's how I get the opposite configuration. So these two are a pair of enantiomers, these two are a pair of enantiomers, these two, and these two are also a pair of enantiomers. If I take any one of these molecules, though, and compare it to the other ones, those are all pairs of diastereomers. I could take this structure here, just circle them randomly, and compare it to any other one. So maybe we'll just compare it to this one. What's the relationship? Well, they have the same configuration at one or more of the centers, these two, but they have the opposite configuration also at one or more of the centers. That's what gives me a pair of diastereomers. So when I have a series of stereoisomers for a given structure, it can only have one enantiomer, but it can have many diastereomers, because any combination where some of the chiral centers are the same in both structures, but one of the chiral centers is different in both structures, is going to produce a diastereomer, because they will no longer be mirror images. Any questions about that? So most molecules have a lot more diastereomers than they have enantiomers. And so this leads us to another of the quiz questions, just drawing a pair of diastereomers. So there's many examples here that could be correct. So if I just draw one structure and maybe put some groups here. So maybe here I'll put an ethyl group, and here I'll put a methyl group. Without, actually, let's make this a little simpler. Let's say I drew something like this that only has one chiral center. I'll just put a chlorine here to make it simple. So I've got chlorine, a methyl, a propyl, and a hydrogen. If I only have one chiral center, assuming we're not talking about cis-trans diastereomers, if I only have one chiral center, there's not going to be any diastereomers. Because if there's only one chiral center, the only way I could make a stereoisomer of that would be to swap two of the groups at that chiral center. And that creates an enantiomer. These two are now mirror images, non-superimposable mirror images. So if I want to create a pair of diastereomers that are not cis-trans diastereomers, I need at least two chiral centers. So if I have a structure with two chiral centers, like this one, that little thing there messed me up, so I'm going to redraw it. Right, this chiral center here has an ethyl, a methyl, and then a sec-butyl and a hydrogen. This one right here has a methyl, an ethyl, a sec-butyl, and a hydrogen. So they're both chiral, two chiral centers. So this molecule has a stereoisomers. If I swap the configuration at one of those two centers and swap the other one, I would potentially be creating an enantiomer, assuming that those two structures are not superimposable. But if which I would need to check to confirm that they're enantiomers. But if I swap the configuration at one center and keep the other center the same, that's when I get diastereomers. So now these two structures are not superimposable, and they're also not mirror images, which means the relationship between them is that they're a pair of diastereomers. But you could have drawn a variety of molecules there as long as they had more than one chiral center and the configurations were the same at some centers but different at other centers. They'd be diastereomers. So this leads to Kristen's question, which is number 5.22 from the textbook. So here we see two different molecules. We want to determine the relationship between them. So just by looking at them quickly, I see they have the same bicyclic parent chain. The only difference is on one molecule, the OH group is pointing in one direction. On the other molecule, it's pointing in a different direction. So the only difference between them is a spatial difference, right? The OH is on the same carbon of the parent chain in both structures, so there's no connectivity difference. So they're definitely not constitutional isomers. Can I superimpose them upon one another? So can I slide this molecule over or flip it over in space and then slide it over, or rotate one of the single bonds and slide it over and get everything to line up? And the answer is no. So they're not superimposable, so they're not identical. The only difference between them is the spatial positioning of the OH group and the hydrogen on that carbon in space. So they are stereoisomers. But more specifically, since stereoisomers is a term that includes both enantiomers and diastereomers, we need to determine if they're enantiomers or diastereomers. And this hint here is important. If you overlook the fact that there are multiple chiral centers here, you might incorrectly think that they're enantiomers, because if this is the only chiral center I notice, and I determine whether this one is R or S, if I did, this would be my top priority group, my second priority group, my third priority group. I have to imagine the hydrogen is pointing behind me by kind of rotating the molecule in space or bringing myself up over top of the molecule so I can see it from a perspective where the hydrogen is pointing away from me. And if I do that, I'll go counterclockwise, which means that this is S. Much easier to see with the model, so you can actually position the model in your hands with the fourth priority group pointing away. If I do the same here, I'll find out that this one is R. So if I incorrectly assume that there's only one chiral center and that they have the opposite configuration, they would be enantiomers. But that's not the case. They're actually diastereomers, because in reality, this is a chiral center, and so is this. And these two chiral centers in the two structures have the same configuration. Right, so we could just look at this one here and we'll confirm it's the same as this one. Right, so if I were prioritizing the groups here, I've got a CH2 here and a CH2 there. They're the same, and a CH2 there. So the first layer out, they're all the same except the hydrogen that's pointing at me. So that's my fourth priority group. So then to differentiate between these CH2s, I got to go to the next carbon. Over here, the next carbon over has an oxygen. So that's going to take priority over anything that's got something that is only bonded to carbons and hydrogens. So this is my top priority. This CH2 is bonded to a carbon. It's bonded to a carbon, and a hydrogen. This CH2 is bonded to a carbon that has two carbons, or two hydrogens, and only one carbon. So if I go up toward the top carbon here, the next carbon over has got more carbons and fewer hydrogens than if I go down to the left, the next carbon over has more hydrogens and fewer carbons. So this is my second priority, and this is my third priority. So in this case, the hydrogen's pointing out at me. So when I go from 1 to 2 to 3, and I find that that's counterclockwise, that would only be S if the fourth priority group is pointing away from me. When it's pointing out at me, I get the opposite, which is R. And if I do the same thing over here, I also determine that's R. So if some of the configurations are the same between the two structures, and some of the configurations are the opposite between the two structures, that tells you that they are diastereomers. Any questions about that one? Alright, so this other quiz question a lot of people were chattering about on Discord. That's good. I like to see that you all are communicating and collaborating. So this one, there's a couple different ways you can approach this. My recommendation, especially since you're allowed to use your model kit during all of your exams, including the final exam this semester, is to work with your model kit as much as possible. It really does make things a lot easier to see. So if you made a model of this one and you made a model of this one, and you held those two models in your hands, and then you just took one and flipped it over like a pancake, everything would line up between the two structures. So these two structures are actually identical. They're superimposable on one another. That's their relationship. They're not isomers. They're the same structure. And so if you don't make a model, here's one way to help you kind of see that. If a group is pointing out at you, just take your fist, make a fist and stick your thumb out toward your face. Imagine that's a group on a molecule pointing, your thumb is pointing out at you. If you flip your fist over like a pancake, your thumb's obviously pointing away from you. So any group that's pointing out at you in a current structure will be pointing away from you if you flip the structure over. And so if I were to flip this structure over, also by flipping it over, I'm just taking like the right hand side of the molecule and flipping that up toward me and then over back into the plane. If I flip this over, it will now be on that side, and my ring will look like that. This group will be here, and this group will be here. And anything that was pointing out at me is now pointing away because of the nature of flipping the structure over. Anything that's pointing away is now pointing out at me. And so now these you can more easily see that these structures are identical. So if you cannot see in your mind how flipping this structure over makes it look like that one, you should definitely be working with the models. You don't need to rely on your brain to do that in a two-dimensional space on a piece of paper. It's very difficult without a lot of experience. So there's no shame in working with the models. I know it takes a little while to put them together. You don't have to put every hydrogen on every carbon and take the time to do that. Just make a ring. You don't even have to put these chlorines on here. As long as you have a different color atom here to differentiate from this one, and you do the same in both structures, you can do this analysis without taking forever to put something really complicated together. So that's what I would recommend with that type of structure. All right, so if I've got a lot of chiral centers in my molecule, I have a lot of isomers, right? We saw that with only 3 chiral centers, we could create up to 8 isomers. If you look at the mathematical relationship between the number of chiral centers, which is n, and the number of resulting stereoisomers, we just saw an example where there were 3 chiral centers, and the number of isomers that resulted, stereoisomers specifically, was 8. And that's because 2 to the third equals 8. 2 times 2 times 2. So you can imagine, because this is an exponential relationship, if I have a molecule with 4 chiral centers, how many stereoisomers could that give? Well, it would be 16. So by just having one more chiral center on the structure, I now have up to 16 stereoisomers. How many stereoisomers can this cholesterol molecule have? Well, we got to count the chiral centers. We got 1, 2, 3, 4, 5, 6, 7, 8. Is this a chiral center? No, it's got 2 identical methyl groups, so it's not a chiral center. Let's just double check through here. Are there any other chiral centers anywhere? All these other carbons don't have 3 unique atoms attached. 4 unique atoms attached. So if I've got 1, 2, 3, 4, 5, 6, 7, 8 chiral centers, 2 to the 8th is the maximum number of stereoisomers, and 2 to the 8th, plugging that into my calculator, ends up being 256 stereoisomers. There are obviously many more than that constitutional isomers for this structure. Right? I could disconnect any methyl group and put it anywhere else on the structure, or take the OH and put it anywhere else on the structure, or make this ring a 6-membered ring instead of 5, and you make this methyl group part of that ring. There's lots of different ways I could change the connectivity of the atoms and make thousands of different constitutional isomers. But there are still a lot of stereoisomers that would only be different, where maybe in one I take this methyl group and have a dash wedge, in another I take this methyl group and have a solid wedge. Right? I'm just changing the direction and space that these groups are pointing in, and it creates a ton of different possible stereoisomers. If you have an even number of chiral centers, if n is an even number, you will probably not have as many stereoisomers as this calculation predicts. Because when you have an even number of chiral centers, as we're going to see a little bit later, some of the stereoisomers will actually be superimposable upon each other, and they'll be identical. Right? So this number assumes that when I imagine every combination of solid wedge and dash wedge at every chiral center, that creates a unique structure, and sometimes it doesn't. And so we'll see an example of that, a couple examples here as we go forward. All right, so let's take a look at cis and trans dimethyl cyclohexane. So we said last time, if my compound has only one chiral center, and we added to that, or an odd number of chiral centers, then the structure will be chiral. It will not be superimposable on its mirror image. That's what the definition of chiral means. It's not superimposable on its mirror image. And it will rotate plane polarized light in one direction or another, equal opposite direction from its enantiomer. If my compound, though, has an even number of chiral centers, it may or may not be chiral. So sometimes, if I have an even number of chiral centers, when I make the molecule three-dimensionally, it ends up being superimposable upon its mirror image. So it's not chiral. Right? So that's ultimately the definition of chirality. So let's take a look at these two examples. Right? So here, I've got a chiral center here. I've got a methyl group, a CH2, and a CH3, and then I've definitely got a hydrogen. Here I've got a chiral center, same analysis. Here I've got one, and here I've got one. So this molecule has two chiral centers, and this molecule also has two chiral centers. One of these molecules is chiral, though, and the other is not. So I want to make sure we can get to that answer by looking at the analysis. So there's a couple different ways to do that before we get there. The ultimate test that should never fail you, assume you do it correctly, is to draw the mirror image of the structure, or make a model of the mirror image of both structures, the original structure and its mirror image, and see if they're superimposable. Right, so let's just do that. So let's say I put a mirror here. Imagine the structure in the mirror. I've got this methyl group pointing down, so it would be here. And this methyl group is pointing up, so it would be here. Are these superimposable? If they look superimposable to you, you should be working with models, because they're not. Even if I slide this one over, even if I try to line up this methyl group with the other and slide it over, this methyl group is not going to line up with the other one. They're not going to be in the same position in space. So if my two mirror images are not superimposable, they are a pair of enantiomers, and they are both chiral by definition. If I do the same with this structure, though, I see something different. So here, this methyl group closer to the mirror would be reflected to create another methyl group close to the mirror, and the one farther away would also have a methyl group reflecting it in the mirror, And now I see I've created two structures that are superimposable. All I have to do is slide this one over on top of the other one, the methyl groups line right up. So if a molecule, even if it has a chiral center, it will be an even number of chiral centers, can be superimposed upon another molecule that's its mirror image. Neither of those are chiral. They're not enantiomers. Neither of these structures have an enantiomer because only a chiral molecule will have an enantiomer, which will be its non-superimposable mirror image. So another way to do that is to look for a plane of symmetry within the molecule. So rather than drawing the mirror image of the structure and seeing if it's superimposable upon the original structure, look for a plane of symmetry or a mirror plane where half of the molecule is a reflection of the other half of the molecule looking in the mirror. And so that's what we see here. If I imagine a mirror plane in this structure, well, this methyl group looking in the mirror would see its reflection. There'd be another methyl group down here reflecting it in the mirror, but there isn't. So this molecule does not have a mirror plane where half of the molecule is a reflection of the other half. And so that helps me to confirm that this molecule is chiral, in addition to what we just talked about in the last slide. This molecule, though, it does have a mirror plane. It's shown right here, right? If I imagine a mirror right down the middle of the molecule, it will always be right down the middle, half of the molecule looking in the mirror creates the other half. The reflection of this half is the other half. And so if there's a mirror plane where one half of the molecule is a reflection of the other, their optical activities will cancel out. There will be no optical rotation. If I try to draw its mirror image, it will be superimposable upon it, which means the structure is achiral. It's not a chiral molecule. If it's superimposable upon its mirror image, it does not have any enantiomers unless it's chiral. And the term for that is a meso compound. Meso compound is a compound where half the molecule is a reflection of the other half. Or in other words, it's a compound that has an even number of chiral centers, but despite having chiral centers, it is not a chiral compound overall due to having a plane of symmetry that splits the molecule in half. And we already did this a couple slides ago. Yeah, this is the definition of chirality. So this is the ultimate test. I would always run this test. Even if you find a plane of symmetry, draw or make a model of both the molecule and its mirror image and make sure that they are not superimposable. Then you can label them as achiral. Here's another example of a meso compound. Clearly we're basically seeing the same thing. The bottom half of the molecule, if it looks in the mirror, the reflection it would see is exactly the same as the other half of the molecule. So this is the situation where the number of stereoisomers is less than the number predicted by this formula that we talked about. Right, so I recommend you make a model of these, but in this particular situation, where these two OH groups are identical, we want to imagine all the different stereoisomers that could exist, right? So if there are two chiral centers, if there are two chiral centers, n is 2, and 2 to the second is 4. So I should be able to draw 4 different stereoisomers. And we can definitely do that if we imagine each possible combination of solid wedge and dash wedge at each chiral center. And the fourth one would obviously have 2 dashed wedges. So I can draw 4 structures, but are they all actually unique? And the answer is no. So let's label these A, B, C, and D. Which 2 are actually identical here? Anyone answer that? Very good. Yeah, A and D are identical. So for D, I just have to flip it over like a pancake. So I'm not this time flipping the right over the left, I'm flipping the top over the bottom. So if I imagine this molecule flat in the screen, take the top of the molecule and lift it out of the plane and just flip the whole thing over like a pancake, then these dash wedges will become solid wedges and they'll line up right over top of these. So that if I flip it over and then slide it over, it will be superimposed directly upon A. So A and D are actually the same. Can I also say that about B and C? And there the answer is no. So if you are not seeing in your mind that how A and D are superimposable, but B and C are not superimposable, after lecture you should definitely take the time to make these models and see if you can show that to yourself with the models. If you can't, then you should definitely set up a time to talk with me, or we can make these molecules in lab. Remind me to do that, and I can try to help show you that that's the case. But that's the test, to see A and D are not enantiomers. B and C are enantiomers because they are non-superimposable mirror images. A and D are superimposable, so they're not even really unique from one another in any way. So even though the formula predicts 4 different isomers, D isn't really different from A. So really in total, I only have 3 isomers created for that, 3 stereoisomers created for that structure. Alright, so what's the relationship between these two? So this is a situation where I would definitely use a model. It's going to be difficult for me to see this in 2-dimensional space. But if I were to rotate this carbon here, so that this ethyl group rotates down into the plane and the molecule ends up looking like this, that will rotate this methyl group up into a solid wedge position. How can I be sure of that? Well, one way to make sure that I've done that correctly would be to make a model, the most surefire way to do it. Another way would be to just analyze the RNS configuration of these centers to make sure they're the same. Right, so if I look at this carbon, I've got priority 1, 2, 3, going around 1 to 2 to 3 would be clockwise, so this would be R. If I look at this center, I've got priority 1, 2, and 3, going from 1 to 2 to 3. Will give me clockwise, but when the 4th priority group is pointing out at me, clockwise is actually S. So I've got an S here. I want to do the same analysis here though to make sure this is actually S. I got a little ahead of myself, so I would prioritize 1, 2, 3. Okay, that one actually is S. So what I did in my mind to rotate this bond and get the ethyl group down into the plane and bring this methyl group up out of the plane until it becomes a solid wedge is correct. And you could do that with a model, you'd see the exact same thing. So what about this structure here? Well, in this case I'd have to rotate the same bond, but I'd have to rotate this ethyl group down into the plane, and that would push the methyl group back. So that would give me something that looks like this. So let's number these 1, 2, this should be 1, and this should be 2. That should give me the methyl group down, if I'm seeing that correctly in my mind. That's a tough one for me even. So I would really definitely use a model there to check that. But I can also check it by finding the RNS configurations. Right, so we saw that this one was R. So let's make sure carbon 1 is actually R. So prioritize 1, 2, 3, going clockwise. That one is actually R. So that matches up. So I know I did it correctly, at least on that part of the molecule. But this is the test though, because this is the part of the molecule I really moved a lot. So for carbon 2 here, prioritizing the groups the way they are, I'd have 1, 2, 3, and going from 1 to 2 to 3 would give me a clockwise rotation, so this one would be R. And if I do the same thing down here, 1, 2, 3, that gives me a counterclockwise rotation, but when the 4th priority group is pointing out at me, counterclockwise is actually R. So I did it correctly. So I found that the difference between these two is now much more comparable once I rotate them into looking as similar as possible. There's no difference at the R configuration center, but at this S configuration center, the other molecule has the opposite configuration. So when I have two chiral centers, and one of the centers is the same in both structures, this one here, but the other center is the opposite in both structures, that tells me that they are a pair of diastereomers. So that answers the first part of this. What about the second part? Is either one a meso compound? And so we said to identify a meso compound, you need a plane of symmetry splitting the molecule in half. Over here I don't have that, right? I could imagine a plane here where most of this half would be reflecting in the mirror to create most of this, but this solid wedge is pointing out at you. When it looks in the mirror, it would see something else pointing out at you, but it's not. So in this molecule, the right and left halves are not mirror images of one another, so this one is not a meso compound. Over here, however, though, we do see where one half of the molecule, if I imagine a mirror plane right here, is a reflection of the other half of the molecule, where the two methyl groups reflect on one another in the mirror. That one is a meso compound. So this one is achiral. I can draw its mirror image and show that it is superimposable on its mirror image. That would confirm that it's achiral. This one, though, is chiral. And I could confirm that. I could draw its mirror image or make two handheld models, one of the original and one of its mirror image, and I would not be able to superimpose them on one another, which tells me and confirms that that structure is chiral. Every meso compound is achiral. And sometimes there are these rare molecules where the molecule has chiral centers. It does not have a plane of symmetry, so it's not a meso compound, but still it's achiral. So there's one test that always works if you do it correctly, and that is make the model of what it would look like in the mirror, and then see if those two models are superimposable. If they are, it's not chiral. Right, so if I had this structure and I wanted to draw its mirror image, so I could imagine a mirror here, it's looking in the mirror. Whatever's closest to the mirror on one side is going to be closest on the other side. I have this one will be reflecting here. This would be a nitrogen, and it would have a methyl group on it reflecting it toward the mirror. Right, everything's that's close to the mirror is close on the other side. Everything that's a solid wedge is a solid wedge, and that's the nitrogen here. There. Okay. So these two structures are mirror images. I just drew the mirror image of the first one. They have chiral centers. There's no mirror plane within the molecule where one half is a reflection of the other half. But both of these molecules are still identical. And I know that because I can take this one, rotate it 180 degrees so that the methyl group with the solid wedge, I'm not flipping it over yet, I'm just rotating it in space 180 degrees, and that solid wedge will end up here, the dashed wedge will end up there, the nitrogen will come over here. When I do that rotation, then I can slide it up and it lies directly upon the other one. It's much easier to see with models, but drawing the mirror image and showing that it can be superimposed upon the other structure is one way to, the best way to confirm that a structure is not chiral. Because by definition, if it were chiral, it would not be superimposable upon its mirror image. And so we just did. All right, so Fisher projections. Fisher projections are probably the worst way, in my opinion, to show chirality. A chiral center is a carbon usually, could be another element, but it's usually a carbon because it has to be a center that has 4 unique groups attached to it. And in order for those 4 unique groups to create a chiral center, it has to be a tetrahedral shape. A tetrahedral geometry has only, well, that shouldn't be X. I'll just make this C, and then over here we'll put A. Right, so it's got 4 unique groups attached. It has to be tetrahedral, and the reason for that is because it's the tetrahedral geometry specifically that creates a situation where if I drew the mirror image of this, it would not superimpose on it. So I'm going to take a 3-dimensional structure and I'm going to make it look as flat as possible. I'm going to make the angles look like they're 90 degrees when they're really at 109. I'm going to take away all the 3-dimensional information and try to make it look flat. But then somehow you in your mind have to imagine some of these groups pointing out at you and some pointing back. And then if I take a chain with an even greater number of chiral centers, it makes it even harder because now I don't have the ability to show a bunch of atoms in the same plane. I'm imagining the ones vertical with dashed wedges and the ones horizontal with solid edges. It's very difficult to create a mental picture of that in your mind. So Fisher projections, in my opinion, are completely obsolete and should be abandoned forever by all organic chemists. So if you can't tell, I have a strong opinion about them. So I will not be giving you any questions about Fisher projections except for one type of question, and they are good for one thing, even though I think on net overall they're bad because of all the other reasons. But the one thing they're good at is comparing pairs of molecules. And that is because if my chiral centers are represented in this way that takes away all of the three-dimensionality of in how they're represented, the direction that the groups are pointing, right or left, does indicate solid wedge or dash wedge basically. And so if I had 2 structures where each chiral center, the groups attached are pointing in opposite directions from those chiral centers, that means those 2 centers have opposite configurations. And so if that happens at every carbon, that means they're enantiomers. If it happens at one or more of the carbons where the bromines are pointing in opposite directions, so they have the opposite configuration, but at some of the other chiral centers they still have the same configuration, then I know they're diastereomers. So the only thing you would need to be able to do with a Fisher projection is to use it to differentiate between pairs to determine if those pairs are enantiomers or diastereomers. And then we're not going to focus on those any more than that because they don't really give us any really, they really make it harder to see the 3-dimensionality of the molecule, which is what we're trying to analyze. So, a little bit more detail about chirality. So as we were saying, a chiral molecule is one that is not superimposable on its mirror image. So any structure I have, if I want to do this test, I could try to draw its mirror image. So we could even imagine a Newman projection. So here I've got a methyl group coming off of this carbon. Down here I've got a methyl group coming off of the other carbon down here. And the relationship between these methyl groups is they're at a 60-degree dihedral angle, which means they're gauche. So the question is this gauche representation chiral? So if I want to know the answer to that, I'd make a mirror image, or make a mirror, and draw what the mirror image would look like. So this one would have the one methyl group reflecting the other in the mirror, and the other one would be pointing down here, reflecting this one in the mirror. So once I draw the mirror image, then I want to see if they're superimposable. Can I take this structure, slide it over, or flip it over, and then slide it over, and see if they're superimposable? If I do that, I find that they are not superimposable. So if a structure is not superimposable on its mirror image, it should be a chiral structure. The problem with that analysis, though, is you have to also consider, when you're doing this analysis, you have to consider rotations of the single bonds. Because the single bonds can rotate freely. So even though these structures are not superimposable, if I imagine them sitting there, I can't just imagine them sitting there, right? This molecule is butane. It looks like this, or it could look like this. If one of these methyl groups is coming out at me and the other is pointing away, this is exactly what we're looking at. This is the gouge. Actually, I should probably draw it like this if I want to look exactly like what we're looking at. If I'm looking down this axis, one of these is pointing out at me, or one is pointing to my right, and the other is pointing to my left a little bit. So this is the gouge version. So it's just a bond line with wedges rather than a Newman projection. I have to remember, though, that the single bond can rotate. And so if I can rotate the single bond in one structure and get those two methyl groups maybe both pointing back, which I can do, and I can also rotate the single bond in the next structure and get those methyl groups pointing back again, now I can see that they are superimposable. So it takes a little bit of extra effort sometimes. If you're doing this test to see if this molecule is chiral, so there's a couple different tests you can do. One is if you look at the structure and there's no chiral centers at all, it shouldn't be a chiral structure. Normally a chiral structure needs at least one chiral center. If I don't have any chiral centers, I can say, well, it's not chiral. But really, this is the definition of chirality. Is it superimposable on its mirror image? If it's not, it's chiral. So when I draw the mirror image, I have to remember that the single bonds can rotate, and these methyl groups would end up being able to rotate around as the single bond rotates. And that means they actually are identical or superimposable in one or another rotation. So they don't have to be superimposable in every rotation, as long as in one rotation on each molecule they look identical. It can be or can be completely aligned on top of one another. That means that they're not chiral, and that's why the optical rotation is 0, because it's an achiral structure. It won't rotate plane polarized light as plane polarized light is passing through a sample of the material. So even if one version or rotation of the molecule should be optically active, if it can interconvert with the opposite rotation or its mirror image, that will cancel out on net, and I won't have any overall rotation of the plane polarized light. So it's like a mixture of enantiomers, but they're interconverting constantly. So there's no way to separate one enantiomer from the other. And we see the same thing here. Right? So if I look at this, if I have cis 1,2 dimethyl cyclohexane chair, the chair conformation is the most stable conformation for this molecule. This is what it would look like. If I look at the Hayworth projection, I can quickly see that it's a meso compound. I can't really see that in the chair. There's no plane of symmetry where this methyl group reflects onto the other in the chair. The chair is not symmetrical. This chair looks chiral. It actually is chiral. But the molecule is not chiral. So as long as there's any one rotation where there's a mirror plane that splits it in half and one half the molecule is a reflection of the other, it's a meso compound, and it's achiral. If it's truly achiral, it should be superimposable or interconverting with its mirror image. All right, so we just saw here, this molecule can't be superimposed upon its mirror image, but they can be converted into one another by simply rotating a single bond. So if I can take this molecule, which is what the molecules actually look like, because the flat structure, none of the molecules are actually going to actually exist in the flat structure. Even though the flat structure is definitely achiral because it's a meso compound, none of the molecules actually look like this. It would create too much angle strain. There'd be torsional strain between adjacent groups on adjacent carbons, eclipsing one another. So the chair is really the way that this molecule truly exists. So if we want to really analyze it, we better be able to show that the true structure can interconvert with its mirror image, so we know that it's not actually distinct from its mirror image, and we can actually confirm it as being achiral. So to do that, we'll talk about doing that here. So this chair conformation is chiral, except for the fact that it is able to interconvert with its mirror image, which actually makes it achiral. So that's what we want to make sure we can walk through that analysis. So it's not superimposable on its mirror image. I could make its mirror image here. I'll put a mirror here. Do my best to try to draw this as the mirror image of the original structure. Right? Does methyl groups reflect? The methyl groups reflect. The top of the head of the chair reflects. The feet of the chair reflects. So I've drawn the mirror image. I can take this molecule and I could make a model of both. I could try to like slide one over top of the other, maybe even flip it over. Without rotating any of the carbon-carbon bonds, they're not superimposable. So it is not superimposable upon its mirror image unless I start rotating the single bonds. It has two chirality centers and no plane of symmetry, so it doesn't look like a meso compound, at least in this conformation. So if I imagine that if it were true that the chair is locked into that conformation, it can't flip to the other chair or ever become flat, it would be a chiral compound. But it's not a chiral compound because it can interconvert readily at room temperature with its mirror image. Since it can interconvert with its mirror image, it is not chiral. It is achiral. And so let's make sure we understand how it can interconvert with its mirror image. And again, this is much easier to see with a handheld model. So I encourage you to make a chair, put one methyl group in an axial position, one in an equatorial position on the very next carbon, then do the ring flip. So rotating the single bonds, just flip the feet of the chair up and flip the head down. And you'll get this, right? The axial methyl group will become equatorial, so we'll call this methyl group 1 and this methyl group 2. Methyl group 1 will end up here. Methyl group 2 will end up here. Notice they're both pointing up though. These are both solid wedges. Neither one is pointing down at all. Straight up and up slightly but out. Straight up slightly but out. Right? So the axial up becomes equatorial up, and the equatorial up becomes axial up. So then, this is also hard to see without a model, I've got to rotate this in space. So if I just hold it on the top and rotate it by flipping this structure, flipping it around this way, I'll end up with the molecule looking exactly like the mirror image of the original structure. And if you're not seeing that, which you're probably not, because I don't think I would see it either, if I didn't already know what it looks like with the model, I highly encourage you to look at a model of this, do the flip, rotate it around, and notice how it looks like the mirror image of the original structure. So if a molecule can interconvert with its mirror image, it is achiral. It has to be unable to interconvert with its mirror image by flipping the structure over or rotating any of the single bonds involved in the structure. And we also know that even though the flat structure does not exist, the flat structure is a rotation of this structure. So if I rotate it out of a chair into the flat structure and I had the two methyl groups sticking out at me a little bit, well, there's a mirror plane right here. So when one half of the molecule is a reflection of the other, that also confirms that it's a meso compound, which is also achiral. So there's a couple different ways I can do that analysis and confirm that that structure is achiral overall. All right, so the next section is about lab stuff, like how do I deal with a situation where I have enantiomers. So we were saying in the beginning how enantiomers have identical physical properties. The only difference is one is a mirror image of the other, so they have the same polarity, they have the same intermolecular forces. There's no way to separate them by distillation because they have the same boiling point. There's no way to separate them by recrystallization in almost every case because they have the same solubility in different solvents and they pack together in crystals with the same geometry for the most part. How can we separate or purify an enantiomer? And maybe even before we talk about how, we should ask why we would need to. Well, we need to separate enantiomers anytime our pair of enantiomers is related to a pharmaceutical medicine, because like we were saying when we first started talking about stereochemistry, if one of my enantiomers has the molecules positioned in just the right way in space to go inside the body and interact with some enzyme and position its groups in the cavity of the enzyme to make this connection and have this medicinal effect, if the enantiomer comes in and its groups aren't positioned spatially in the same way, it won't interact with the same enzyme. Chances are it might have some undesired interaction with a different enzyme and cause some undesired side effect. So it's often the case that when an organic chemist is making a new pharmaceutical drug, they're trying to make one enantiomer because that has medicinal properties. But in most organic chemistry reactions, the process of making that molecule can't strictly make the one enantiomer they want. They often also make the other enantiomer. So it's very common for a reaction to produce a pair of enantiomers. And then you're in a position where you have to separate them because one has medicinal properties and the other creates some undesired side effects that are unsafe or possibly very hazardous. So how can we separate or purify enantiomers? Well, there's a couple different ways that's been done. So here's the first one that occurred in 1847 by Louis Pasteur, who noticed that this racemic mixture of these two tartaric acid salts, so these two molecules are enantiomers. How do I know that? Well, I've got two chiral centers. At the first chiral center, the OH is pointing in the opposite direction from the first chiral center in the other molecule. At the second chiral center, it also has the opposite configuration. The OH is pointing in opposite directions. So they have the opposite configuration at every chiral center, and if I made models of them, I could show that they're not superimposable. So I know that these are enantiomers. And this was a nice discovery, but it was relatively easy to do because it's a very rare situation where the spatial differences between these molecules cause them to pack together differently to create differently shaped crystals, which could be separated with tweezers. So it's not often the case that you can just pick one of the molecules out from the other, especially when the only difference between them is a spatial difference, and especially when they're mirror images. So this is not going to work for most pairs of enantiomers because most pairs of enantiomers don't produce differently shaped crystals. They produce the same shaped crystals because the molecules have the exact same shape except they're mirror images. So that approach doesn't apply to most situations. Another approach is to use a chiral resolving agent. This does a chemical reaction and converts my enantiomers into diastereomers. So if I have a pair of enantiomers where they have a different configuration at every chiral center, in this case there's only one chiral center, and one of these is S and the other is R. So what's happening here is there's an acid-base reaction, so the lone pair of the base is going to pick off this proton, so I'm going to just show the proton bonded here so we can show the curved arrows. So the base picks up the proton, the electrons the proton was sharing stay behind to create the negative charge on that oxygen. Same thing here. That creates a negative charge on that oxygen. So I have not done anything to change any of the bonds at these chiral centers. So this one's still S and this one's still R. What I've done though is created a salt. So the positive-negative full charge attraction in the solid state is going to cause these two structures to basically bind to one another and stick together. So even though this molecule only has one chiral center and its enantiomer has the opposite configuration, so they have the same physical properties, once they're combined with this other counterion that's also chiral, that combination of them being stuck together so strongly with the opposite charges attracting in an ionic bond actually creates a situation where they kind of behave like one molecule. And so now I've basically got the equivalent of one molecule here and one here. And in this top molecule, I've got an S configuration here. Over here, if I prioritize these groups, I've got an S as well. Doing the same thing here, this is also going to be S. So now I've created a pair of diastereomers because they have the same configuration at one of their chiral centers. These are both S, but they have the opposite configuration at the other. So what's the advantage of converting a pair of enantiomers into a pair of diastereomers? Well, enantiomers have all the same physical properties. Diastereomers have some differences in their physical properties. So now there might be a difference in solubility between this salt and this salt, or a difference in melting point, or something like that. So maybe I could do a recrystallization, and one of these would crystallize in a solvent before the other. So then I just have to, after I separate them, because now they have different properties, I just have to remove that proton again and recover the individual enantiomers separate containers from one another. So that takes advantage of the fact that diastereomers have different properties, whereas enantiomers have basically all the same physical properties. And the third way to separate enantiomers that we're going to talk about, so if I ask you a question about separating enantiomers, you could talk about the rare example where the enantiomers produce differently shaped crystals. You could talk about the last example we just looked at, where you can convert a pair of enantiomers into a pair of diastereomers by running a reversible chemical reaction. The diastereomers have different enough properties to separate, and then you can reverse that chemical reaction and reform the enantiomers separate from one another. The third example is a type of chiral chromatography. So we've talked about affinity chromatography and ion exchange chromatography, especially in the case of affinity chromatography, and that's an example of that is TLC. So in the TLC demo and in your questions from lab 3 that you're answering about silica gel affinity chromatography, normally we make a spot, we dip that in a solvent, the solvent runs up the paper, and depending on how polar the material was in the spot, if it's very polar, it sticks and doesn't travel very far. If it's not as polar, it doesn't attract to the silica gel very much, and it travels further up the plate. So affinity chromatography takes advantage of attractions between the material and the plate, and that would be based on the polarity of the structure. That's not going to work to separate enantiomers, because enantiomers have the same polarity. The difference between these two structures is not a difference in polarity, it's just a slight difference in the spatial positioning of the chlorines. So the only way to separate these through chromatography is to create something different from silica gel that can resolve the enantiomers or attract one enantiomer better than the other. So instead of standard silica, what I would do is I would create a plate, or I could do this on a larger scale with a tube, like a column, and I would put on the surface of that plate or on the inside of this column a material that has some three-dimensional specificity to it. So I would create a material that's got little cavities in it, and those cavities maybe position an OH group, or a charge, or maybe a low polarity group in a certain position in space, so that when one molecule attracts to it, because of the spatial positioning of the chlorine, it attracts better, because things, it would be probably a better example if I drew a molecule that had more sites to attract, but if I've got a couple sites to attract here, if those sites are positioned at a certain distance from one another, a certain spatial arrangement, it can come in and attract in this cavity in a very specific way. So I can get one molecule to attract to the material in the column or the material on the plate. I can get one molecule to attract to that better than the other because the spatial positioning of the atoms, the only difference between those two enantiomers, allows one to line up with the specific spatial positioning of other atoms on the material that's packed in that column or on the silica plate. Well, it wouldn't be silica, but on the TLC plate. So chirochromatography allows you to attract one enantiomer better than the other. So one enantiomer will travel up the plate faster than the other or run through the column faster than the other, and they can be separated because of their difference in attractions to the material on the plate or in the column. But again, the material has to have pockets or sites of attraction that position groups in a very specific three-dimensional way so that they can line up and attract to a group that has an attractive site with a solid wedge versus a dashed wedge. It's a very subtle art, and it's a relatively new development, and it's still continuing as an area to separate enantiomers, because if pharmaceutical companies really need to separate enantiomers for their pharmaceuticals because of the need to only administer a drug if it has a medicinal effect and not to include the enantiomer if the enantiomer creates side effects. Obviously, people don't want that. All right, so that's it for Chapter 5. And we need to get a little bit into Chapter 6 today to stay on track. Chapter 6, in large part, is a review of General Chemistry 2 topics. So that may be a relief to some of you. It may be a worry to others of you, depending on what your Gen Chem 2 experience was like. But we're going to talk about enthalpy, we're going to talk about entropy, so that we can use these factors to help us predict and explain organic chemistry reactions that we're going to get into in Chapter 7. So if you recall from Gen Chem 2, enthalpy is a way of measuring heat exchanged between the system and the surroundings. It's also a way of measuring a potential energy change for a situation or a reaction. So one of the simplest types of processes we can talk about is just simply a bond breaking. We know energy is required to break a bond, and that's because there's a potential energy difference between the energy for the electrons when the bond is broken versus when the bond is formed. Right? We talked about molecular orbitals. We know that a bonding molecular orbital has a cloud of electrons that surrounds both nuclei, and so the electron cloud and the construct of interference right between the nuclei will form nice attractions there, and that will be lower in potential energy than the electrons would be if they stayed separated around their individual nuclei. It's not as stable. So the quantity of potential energy difference between the stability of the bonding molecular orbital for the electrons versus the stability of the individual atomic orbitals for the electrons, that's the amount of energy that will have to be supplied from the surroundings in order to break a bond. Right? So bonds always have to absorb energy. That's a positive value for delta H in order to break a bond. I have to put energy in. The system has to absorb energy from the surroundings to break a bond, because I can't just break the bond and have the system go up in potential energy unless that energy comes from somewhere. It has to come from the surroundings. You can't create energy out of nothing. Typically, when we're talking about a bond breaking, we're talking about homolytic cleavage of the bond, meaning one electron goes with this atom, one electron goes with that atom. We could also imagine something called heterolytic cleavage, and that's where both electrons go in with the same atom. This actually happens fairly often. The energy associated with that may be a little bit different. So just to be consistent, when we're talking about breaking of bonds, we're pretty much always talking about breaking the bonds homolytically. If we're listing the bond dissociation energies or the amount of heat or energy required to break a bond, we're talking about breaking it homolytically unless otherwise noted. Notice that when we show in single, so we've got two electrons in this bond. If a single electron moves, we use this fishhook type arrow. The arrow has only one extra line on its tip instead of a tip that has two lines. Right? So the two lines indicate a pair of electrons moving. A fishhook type arrow with a single barb there, that is representing a single electron moving. So one electron ends up on here instead of a lone pair. So this is the type of situation we're talking about if we're talking about strictly how much energy does it take to break a bond. And different bonds obviously require more or less energy to break. Usually we're looking at these in kilojoules per mole. The ones with the higher values are the stronger bonds. They take more energy to break. If I want the hydrogen to grab an electron, the fluorine to grab an electron, I need a lot more energy there. So that tells me that the bonding molecular orbital for these two is especially stabilizing compared to a situation where the hydrogen has one and the fluorine has one, and their orbitals no longer overlap to create the constructive and destructive interference, creating the bonding molecular orbital that stabilizes the electrons. So this tells me how much the electrons are stabilized in their bonding molecular orbitals as well. Notice that carbon-carbon bonds vary a little bit in strength. So typically, if we're going to do calculations with these, we will use the average amount of energy in a specific type of bond to do the calculations, and that's going to give us an estimate. It's not going to give us an exact energy associated with a reaction. If a bond breaks, I have to put energy in. What if a bond forms? Well, obviously, I can't create or destroy energy. So if I have my electrons in individual atomic orbitals, and then those orbitals get close enough to overlap, so now the electrons can exist in a microorbital, it's going to go down in energy. I'm going from a higher potential energy state, because there's the potential for them to get closer and attract, to a lower potential energy state. And so going from more energy to less energy, the energy's got to go somewhere. It ends up leaving and going into the surroundings. And so forming a bond is going to release energy into the surroundings. That's exothermic. The energy leaves the system and goes into the surroundings. And so if breaking an HF bond requires 569 kilojoules to be absorbed, forming an HF bond would release, or would be negative 569 kilojoules. So make sure you understand the sign conventions there. All right, let's make sure we understand these concepts from Gen Chem 2. Try to clear common types of confusion by looking at a couple examples here. So we want to talk about, for these examples, the heat energy that's exchanged, right? We're never going to create or destroy energy. It could go from the system to the surroundings, or from the surroundings to the system, right? So if it goes from the system to the surroundings, the system is losing energy. That's negative from the point of view of the system. And if we don't say specifically, we can assume delta H is for the system. If the opposite is the case and it goes from the surroundings into the system has to absorb energy. That is going to be endothermic, because we're pretty much always looking at it from the point of view of the system. The system loses energy, it's going out. Exo means out. Like an exoskeleton is on the outside of an insect. If the system absorbs that energy from the surroundings, it's going in, it's taking the energy in, or it's having an increase in the amount of energy it has. All right, so I've got hydrogen and fluorine free radicals coming together to form a bond. Anytime a bond or attraction forms, it's always exothermic. It's because it goes from a higher potential energy to a lower potential energy. Forming a bond releases potential energy because it's more stable or lower in potential energy. Once the bond forms, there isn't the potential to form it anymore. If I break a bond, it's always endothermic. It has to absorb energy. There's an attraction there. I have to break or overcome that attraction. Some type of collision with enough kinetic energy from the surroundings has to occur so the system can absorb that energy. And also, when I go from a relatively stable situation to an unstable situation where now the atoms, orbitals are no longer overlapping to create the bonding molecular orbital that stabilizes those electrons, I'm going from a low potential energy to a high potential energy. And so the only way I can increase the potential energy, I can't just create it out of nowhere. It has to come from the surroundings. And that's why the system has to absorb energy. So if all I'm doing is forming or breaking, it's always negative or positive, respectively. If I'm both breaking a bond and forming a bond, then it depends on their relative strengths. Right? So if I'm looking at a reaction coordinate diagram and I'm looking at the potential energy, if the bond is strong to begin with, so we're not talking like a strong acid. If an acid or base is strong, it's very unstable and very reactive. If a bond is strong, what we mean is it's holding things together tightly. It takes a lot of energy to break it. It's not unstable. It's strong and held in there. And so that's a stable situation with low potential for change on its own. So that'll be a low potential energy. If it's strong, I have to put in a lot of energy to break it. It's starting at a low potential energy. So that would be a situation where I have to put a lot of energy in to break it, but then when the new bond is formed, that releases energy. But if it's not a very strong one, it's not going to release that much, or it's not going to be that stable. So on net, I still have an endothermic process. Conversely, if I'm starting with a weak bond, it's not very stable. There's the potential for the electrons to be more stable if it were to rearrange. That would be relatively high in potential for change. And if it forms a much stronger bond, first I have to break that, so I have to put some energy in. But if it forms a stronger bond that's lower in potential energy or lower in potential to change, that on net is going to release energy. So that's going to be exothermic, or a negative value for delta H. Most reactions obviously involve both bonds breaking and bonds forming. The energy associated with each bond is relevant. Each bond that breaks requires some energy to be absorbed. Each bond that forms requires some energy to be released, so it depends on the specific energy values. We can determine what's happening if we look at the temperature, because the temperature is always a property of the surroundings. And if we have a temperature change, that tells us specifically about the kinetic energy of the surroundings. So if I do a reaction and I observe the temperature is decreasing, that tells me that the kinetic energy is decreasing in the surroundings. So the surroundings doesn't have as much energy as it had anymore. And so that tells me that the surroundings must have given energy to the system, or that the system absorbed that energy. And so just by looking at the temperature change in the surroundings, I know the enthalpy change for the system has to be positive. And that would be a situation where strong bonds are breaking and being replaced with weaker bonds, or strong attractions are breaking and being replaced with weaker attractions. So then obviously the opposite is true. If the temperature is measured to increase, that tells me that there's an increase in the kinetic energy of the surrounding. Where did that energy come from? It can't be created out of nothing. It had to have come from the system. So the enthalpy change for the system is negative. It's losing that energy. It's going into the surroundings and being expressed as kinetic energy for the surroundings. And so that would be a situation where the reaction is releasing energy because it's going from a higher potential energy to a lower potential energy, and that energy difference is being released. And so that means it's becoming more stable when the products are formed, because they're lower in potential energy as the difference in potential energy is released. So you definitely want to make sure that this all makes sense to you, and that if you can apply it to specific examples. We just showed those on the previous slide. So real quick, why do we care what the sign is for delta H? Well, if you're performing a chemical reaction in the lab and you know delta H is positive, you need to make accommodations for that. If you know that the reaction has to absorb energy, you'd probably want to use a heat source. right? If I know that my reaction is going to start at a lower potential energy and then make it up to a higher potential energy, I know it has to absorb heat from the surroundings. I'm going to apply heat. I'm going to put a hot plate or in a sand bath or something like that to provide the heat that the reaction needs. And if I don't, the reaction may not occur and may not have enough energy to get over this activation energy barrier, which we'll talk more about when we talk about kinetics later. And the reaction might not produce significant amount of products. If I'm performing a reaction in the lab and I know that delta H is negative, I know that it's exothermic. In that situation, as the reaction progresses, it's going to release heat. That could actually be dangerous, especially if I do it on a large scale. It's releasing a lot of heat, or if I know it happens quickly and a lot of the molecules are releasing that energy in a short period of time. It could create too much heat for me to deal with. It could cause an explosion, and so I might need to use something like an ice bath to absorb some of that heat so it doesn't build up and cause the liquid to boil or pressure to be created or an explosion or something like that. So there are practical reasons why you definitely want to know whether a reaction is endothermic or exothermic. So here was the last quiz question that related to these topics that you all answered here. So this is a chemical reaction. What's ultimately happening here is one sigma bond, this one right here, is no longer there. This pi bond moves over here and it's still a pi bond, so that's not really much of a change in energy. This pi bond here moves over here and it's still a pi bond, so that's not much of a change in energy. But what's ultimately happening here in terms of the stability of the molecules or the energy is the sigma bond is moving and becoming a pi bond. So if we understand the difference between sigma and pi in terms of how stable they are for the electrons, we can answer this question. All right, so we know a sigma bond between two carbons is where there's head-on overlap between the two orbitals. The molecular orbital that's created surrounds the nuclei and allows the electrons to attract nicely right in the space between the nuclei where the construct of interference is. A pi bond, if you recall, involves side-by-side p orbital overlap, both above and below the plane of the atom. So when those orbitals start to overlap, it creates a molecular orbital where the constructive interference occurs in the areas of overlap. But since there's a node right in the plane of the carbons, the electron density is above and below that plane. It can't get very close to the nuclei, so it's not very stable to have those electrons farther out from the nuclei. So by going from a sigma bond that's more stable to a pi bond that's less stable, what I've done here is to go from a low potential energy, because there's not much potential for change if it's already stable, to a higher potential energy where now there's more potential for it to actually go back. I have to break a bond to get there, and then when the new bond's formed, it goes down in energy a little bit, but since the products are less stable and higher in potential energy than the reactants, on net, the delta H is a positive value for the system. The system has to absorb energy from the surroundings because it takes more energy to break a sigma bond than is released when a new pi bond forms. And then always, if you look at it from the point of view of the surroundings, it has to be the opposite. Right? They can't both go up. Where would the energy come from? It can't be created out of nothing. So if the system is absorbing energy, the surroundings has to be losing energy. Any questions about any of that? All right, well, if there's anyone left on the feed, there's the bullet points for today's content. Lots of good practice for you to do. Again, this, for those of you who have lab Tuesday through Thursday, you'll be tested on this next week. For those of you who have lab on Mondays, it will be the week after. And then on Thursday, we'll be getting into day 12, which will be just continuing with a lot of these General Chemistry 2 topics. If you were in my Gen Chem 2 class, we tried to emphasize the difference between thermodynamics versus kinetics. And we're going to be emphasizing that a lot in this class as well. It's very relevant to trying to predict when you do a reaction, whether you end up with more reactants or products when it reaches equilibrium, versus when you do a reaction, how long will it take to get to equilibrium? And those are two important questions. And we'll see when we start to talk about reactions, starting in chapter 7, how important these concepts are. So I want to try to re-emphasize these in the context of this review to set up our foundation for thoroughly understanding a variety of chemical reactions moving forward. Any questions about anything? All right, well, I'm going to end the recording then.